Dear students, now let's go to part 2 impulse momentum application examples. Before I go through these topics, I shall speak few points on impulse momentum theorem. So you have this handout at hand. Now please read this material before you go to problems. There are many problems examples. So I think from Newton's second law of motion, just force is equal to mass times acceleration, and acceleration is nothing, the change in velocity divided by change in time. So this would mean if you make crisscross, then the rate of change of momentum equals the net force acting on a fluid mass. So please read this material so that you can get the detail, and different solved problems in fluid mechanics also given. Please go through this. And from Bansal, you have many examples. Please, you are kindly requested to go through these examples for clarity. Different examples you have. Now, to start with, what is application? Just what are applications of impulse momentum equation? So you have two major applications. The first one is to determine the resultant force acting on boundary of flow passage by a stream of fluid as the stream changes its direction, magnitude, or force. So if there is a change in direction and magnitude, then you have resultant force will be changed. So for example, pipe bends, reducers, moving vans, jet propulsion. So these are examples of this one. So to determine the resultant force acting on boundary of flow passage. So if you have pipe bend, then there is change in direction of the flow. So you will have resultant force acting on that bend. And the second application is to determine the characteristics of flow when there is an abrupt change in flow section, which is cross-section of the channel or pipe or conduit, etc. So problems of this type: sudden enlargement of a pipe, hydraulic jam in a channel. So these are the major applications of impulse momentum. So you will have equation you can develop with just entry and also exit you can check. So the rate of change of momentum will be changed. So I think the rate of change, just the net force acting on a fluid mass, equal to the change in momentum of the flow per unit time in that direction. So if you have x direction, then you can calculate. Now let's start to the example. First example, which is 5.13. Let us see pipe bend in horizontal or vertical plane. A 45-degree reducing pipe bend is connected to a pipeline. The diameters at inlet and outlet of the bend are 600 millimeter and 300 millimeter respectively. Find the magnitude and direction of the force exerted by water on the bend. If the intensity of pressure at inlet to the bend is 8.829 Newton per centimeter square and rate of flow of water is 600 liters per second, now we will find this one, direction, magnitude and direction of the flow to the bend. So neglect friction losses and take unit weight of water, this one. Now how do you compute? So let us see. So this is inlet to the section. Then there is a bend with 45 degree this direction, but the cross section is 300 millimeter at exit. So what will happen? So if intensity of pressure is given at inlet, intensity of pressure, then flow rate is also given. Then what will be the intensity of pressure at outlet? You can compute. What you are asked, magnitude and direction of the net force. Now let us see. So first inlet parameters, diameter D1, 600 millimeter, 0.6 meter, A1, 514 D1 square, which is this area, 0.2827 meter square. At the outlet section, D2, 0.3 meter, A2, you can compute like this. Then you should be consistent in units of measurement. So you have to change all the dimensions into metric system. So pressure at inlet 8.829 Newton per centimeter square. So if you convert to Newton per meter square, you will find times 10 to the power 4 Newton per meter square. Flow rate, again, 600 liters per second, convert into meter cube per second, 0.6 meter cube per second. Velocity at inlet, we can compute now. So see from continuity equation, velocity is Q over area. Then we can compute 2.122 meter per second. This is the velocity at inlet section, and the velocity at outlet section similarly Q over A2. So cross-sectional area already you have here, then 8.488 meter per second. Now you will apply Bernoulli's equation at section 1 and section 2. So at section 1 you have pressure head P1 over gamma plus V1 square over 2G plus Z1 equal to P2 over gamma plus V2 square over 2G plus Z2 plus head loss. So there is no head loss, neglect head loss between section 1 and section 2. So parameters now you can insert into the equation. Then the only unknown is P2. So the pressure at exit will be computed. So 9.81 kilonewton per meter square. Then since pressure is given in Newton per meter square, to make consistent with the units of measurement, 9.81 kilonewton per meter cube. Then cancel this. Then you will find in meter, then P2 in kilonewton per meter cube. Then you can find kilonewton per meter square. So this is the pressure intensity at exit. 54.519 kilonewton per meter square at exit. So now apply momentum equation. So we are applying the three governing equations. The first one is continuity equation, then Bernoulli's equation, then the third one is momentum equation. So momentum equation, the net force acting on a fluid mass is equal to the rate of change of momentum on that direction. So rate of change of momentum. So you have x direction here. In x direction, you have flow is going, then it will change to this direction. So what will happen? Now, summation of force in x is equal to m dot, which is mass flow rate, times V2x minus V1x. So mass flow rate is nothing, density of the fluid times flow rate. Then V2x minus V1x. So insert in the computation Fx, you can find now Fx, or the force in x direction, will be rho cube V2 cos theta. V2 cos theta, why? Because at exit you have inclination, so you have V2 to this direction, then V2 cos 45 degree, V2 sine 45 degree. But here V1 is horizontal, no component in x, in cosine. So after substitution, V2 cos theta minus V1 plus P1 times area. This is pressure force. Pressure is force over area. Then if you crisscross, you will find the force is P1 A1 minus P2 A2 cos theta. Since at section 2 it is inclined, so you have to calculate cos theta. So Fx will be computed like this. So this is, you will find in Newton, because the density of the fluid is 1000, then in Newton. Or sometimes you may use the equation, sometimes you can use equation of this one, gamma q over g. If you make gamma q over g times this change in velocity, you will find in just in kilonewton. But now first you will find in Newton. Then you can convert into kilonewton. And in y direction, the same rho cube v1y minus v2y. But v1y, no vertical component, so it will be 0. v1y is 0. Then other components, p1 times a1, you have the same. You can compute p2 a2 sine of theta. This is also similarly, you have sine theta because of y direction. But here, no y direction, then you have this component. Negative sign indicates the force in y component is to the downward direction. So most of the time, flow is going to this direction, but pressure may oppose to this direction. You see, due to pressure difference, pressure is to this direction, but at exit, just resistance. P2 is against this direction, but flow rate is the same direction, so that's why the result comes negative. So as exercise, please do this one, 5 bend in just if the bend is 135 degree to this direction, what will happen? So component, you have to construct component, then finally you will find resultant force, this one, and theta, this one. So I hope you will find as exercise. Okay, so this is all about today's tutorial. Hopefully you liked the video, and thanks for watching.